Hello everyone, my name is M. Krishnaveni. I am working as Assistant Professor in Marri Laxman Reddy Institute of Technology and Management. Today I am going to tell about the one important module of the engineering chemistry, water and its treatment. Coming to the important topics in this module, introduction to hardness of water, means what is hardness of water, estimation of hardness of water by complexometric method, numerical problems based on hardness of water, potable water and its specifications and steps involved in the treatment of the potable water, disinfection of water by chlorination, breakpoint chlorination. Next, defluoridation and determination of fluoride ions by Nalgonda technique. Next, boiler troubles, scale sludges and caustic embrittlement. Next, boiler feed water and its treatment. In that, we will learn about calgon conditioning, phosphate conditioning, and colloidal conditioning. Next, external treatment means softening of water by process called ion exchange process, and desalination of brackish water. In that, we will learn about the reverse osmosis. These are the topics which we will cover under the Unit 1 module of the water and its treatment. First of all, what is water? We know water is an universal solvent. Without water, we can live for 1 or 2 days. But the first life on earth has started in the water. The single cell organisms has evolved from the water itself. Okay. All the organisms depend on water for survival. Our human body also will consist of the 70% of the water. That much importance is having water in our daily life. All the plants, animals cannot survive without water for a long days. Now coming to the topic, hardness of water. What is hardness of water? Why we have to test whether the water is hard or soft? If a water is not a hard water, then we can say it is a soft water. But why hardness of water will come to the water, and what are the important factors which will give hardness to water, we will see brief in this topic. Hardness of water is originally defined as the soap consuming capacity of a water sample. The soap consuming capacity of water is due to the presence of certainly salts of calcium and magnesium and other heavy metals dissolved in it. Means, for example, if we take a water sample and if wash our hands with the soap, if we get lather or foam, then we can say it is a soft water. If we do not get any lather or foam, when we wash our hands with certain water with a soap, then the water sample is called as the hard water. It is said to be the hard water. Okay, this is the soap consuming capacity of the water. By seeing a water, we cannot say it is a hard water or soft water. If we wash the hands or any clothes with the water and soap, when foam is coming, lather is forming with the water, then the water is called a soft water. If foam or lather is not forming, then it is called a soft water. The soap generally consists of a long chain fatty acids like oleic acid, palmitic acid and stearic acid, salts of sodium and potassium. Calcium and magnesium react with salts of long chain fatty acids present in the soap to form insoluble scums of calcium and magnesium soap. Means the soap consists of the sodium stearate, means the long chain fatty acids like C17H35CONA, means this is the sodium stearate. This is the chemical formula of a soap. When the soap react with the calcium chloride, this calcium chloride is present in the water, hard water. When these two react, they will form a scum like insoluble calcium stearate. This calcium stearate is insoluble and it will form white scum-like structure on our hands or our body when we wash with the soap. And along with that, NaCl also formed. For example, if the water contain the magnesium sulfate also, it will form the insoluble magnesium stearate, and along with the sodium sulfate, salt is also formed. Okay, mainly the soap which will contain the sodium stearate, it will react with the chlorides and sulfates present in the water, and it will form the insoluble precipitate scums which will not produce the lather. Okay, this is the hardness of water. Next, causes of hardness. Why the water will get the hardness? Why these salts? How these salts will be present in the water? How they will be mixed up with the water? The rainwater on its way to ground. Where we will get the water? Primarily from the rain. When rainwater is coming onto the ground, it will dissolve carbon dioxide gas. The carbon dioxide, little amount of the carbon dioxide gas is present in the atmosphere. This water, while flowing to the beds of soils of rocks containing the carbonates, the rainwater, as it fell down on the ground, it will pass through some soils or rocks which will containing the carbonates. These carbonates react with the dissolved carbon dioxide which is present in the water and forms bicarbonates. This bicarbonate ions causes temporary hardness, means the calcium carbonate which is present in the ground in the form of rocks. This carbon dioxide which is present in the atmosphere will mix up with the rainwater while coming down, and they will form the calcium bicarbonate and magnesium bicarbonate. This calcium bicarbonate and magnesium bicarbonate will cause hardness to the water. And next, types of hardness. We will see how many types of hardness of water are there. The hardness of water is of two types, mainly the temporary hardness and the permanent hardness. The temporary hardness of the water is due to the mainly the bicarbonates of the calcium and magnesium. Okay, which will cause the temporary hardness. The bicarbonates of the calcium and magnesium salts will cause the temporary hardness to the water. This temporary hardness can be removed by simple boiling. The temporary hardness causing salts like the calcium bicarbonate and magnesium bicarbonate can be removed simply by boiling. And next, another type of hardness is the permanent hardness. The permanent hardness due to the presence of chlorides and sulfates of calcium and magnesium. Okay, when the calcium and magnesium are present in the chlorides and sulfates form, means CaSO for calcium sulfate, CaCl2 calcium chloride. When the calcium is present in the sulfate form or in the chloride form, or magnesium is present in the sulfate form or in the chloride form, it will cause the permanent hardness to the water. The permanent hardness cannot be removed easily by boiling. It is removed by the process called the ion exchange process. Ion exchange process. It is one of the important process by which we can remove the permanent hardness causing salts. The temporary hardness causing salts can be removed by the boiling, while the permanent hardness causing salts are removed by the method called the ion exchange method or process. Next, how the temporary hardness causing salts can be removed. The temporary hardness causing salt, temporary hardness is also called the carbonate hardness. Why the temporary hardness is due to the presence of the bicarbonates of the calcium and magnesium. Temporary hardness is caused by the presence of dissolved bicarbonates of the calcium and magnesium and other heavy metals. Heavy metals like iron, magnesium is also present in the water, but they won't cause any hardness to the water. Mainly the calcium and magnesium bicarbonates will cause temporary hardness to the water. What will happen in the temporary hardness? Cause water is boiled to boiling point. These calcium bicarbonate and magnesium bicarbonate which are present in the water, they will be converted into the calcium carbonate along with the release of the CO2 gas and H2O. What will happen? This soluble form of calcium bicarbonate will be converted into insoluble calcium carbonate along with the release of the CO2 gas and H2O. Like that, the magnesium bicarbonate also, when heated, it will be converted into magnesium carbonate along with the release of the carbon dioxide gas. Okay, this is how the temporary hardness causing salts like bicarbonates of calcium and magnesium can be removed by boiling. Next, permanent hardness. This permanent hardness is also called the non-carbonate hardness. Okay, means this permanent hardness is caused due to the presence of the chlorides, sulfates and nitrates of the calcium and magnesium. Next, permanent hardness cannot be removed by boiling. As I told, it cannot be removed by boiling. Permanent hardness is caused by the presence of the dissolved calcium and magnesium sulfates and calcium and magnesium chlorides. The calcium sulfate or calcium chloride, magnesium sulfate or magnesium chloride. These will cause the permanent hardness to the water. The sum of the temporary hardness and permanent hardness is refers to the total hardness. As I told, the temporary hardness, it is indicated simply as TH, plus permanent hardness, it is indicated as the pH. These two hardnesses is equal to the total hardness. Total hardness. Now coming to the units of the hardness. Most commonly, the units of the hardness of water are the ppm, means parts per million. 1 ppm equal to 1 part of calcium carbonate equivalence hardness causing substance present in the 10 to the power 6 parts of water. And milligrams per liter also. We can measure the hardness of water in terms of mg per liter. 1 milligram per liter equal to 1 mg of calcium carbonate equivalence hardness causing substance present in 1 liter of the water. The relationship between the 1 mg per liter or 1 ppm is equal to 1 liter equal to 1 kg equal to 1000 grams equal to 1000 into 1000 milligrams is equal to 10 to the power of 6 milligrams. Okay. This is how 1 milligram equal to 1 ppm. This is the relationship. And Clark degree. 1 Clark equal to 1 part of calcium carbonate equivalent hardness in 70,000 parts of the water. Degree French. 1 degree French equal to 1 part of calcium carbonate equivalence present in the 10 to the power of 5 parts of the water. Means the most commonly used units of hardness of water are the ppm, parts per million, milligrams per liter, degree Clark or degree French. These are the most commonly used units for the hardness of the water. Next, why we will take the calcium carbonate equivalent hardness. The calcium carbonate is the most insoluble salt and the molecular weight of the calcium carbonate is 100 and the equivalent weight of the calcium carbonate is 50. For ease of calculation and for the most insoluble nature of the calcium carbonate, we will take the calcium carbonate equivalent hardness as the standard value. Okay, calcium carbonate equivalent equal to mass of hardness producing substance into molecular weight of the calcium carbonate by molecular weight of the hardness producing substance. Means we will convert the hardness of the substance into calcium carbonate equivalent because of the ease of calculation and it is the most insoluble salt also. Here we can understand it by seeing a simple problem. Calculate the calcium carbonate equivalent hardness of a water sample containing 204 milligrams of calcium sulfate per liter. Means a water sample containing the 204 milligrams of the calcium sulfate per liter water. They are asking to calculate the calcium carbonate equivalent hardness. The calcium sulfate is which type of the hardness causing salt? It is a permanent hardness causing salt. Okay. Now the calcium carbonate equivalent hardness equal to mass of hardness producing substance. How much mass means weight? 204 into molecular weight of the calcium carbonate into 100, and by molecular weight of the hardness producing substance. The molecular weight of the calcium sulfate is 136. If we calculate this, we will get the 150 milligrams of calcium carbonate equivalents per mg per ml or ppm. This is how we will substitute the values in the formula, and we can calculate the calcium carbonate equivalent hardness. And next, estimation of hardness of water. How we will estimate the hardness of water? There are three main methods: soap titration method, O. Henry's alkali method, and EDTA method. The most commonly used method and the popular method is the EDTA method. This EDTA method is also called the complexometric method. First, what is meant by EDTA? EDTA means ethylene diamine tetraesteric acid. The structure is shown here. Ethylene, 2 molecules of carbon, diamine, 2 molecules of nitrogen, tetraesteric acid, 4 molecules of the acetic acid. Okay, this is the structure of the EDTA. The EDTA method is also known as the complexometric method. Why? Because the endpoint is detected by the formation of the complex between the metals and the EDTA. Whatever the salts present in the water will form the complex with the EDTA. That's why it is also called as the complexometric method. The basic principle involved in the EDTA method is when hard water comes in contact with EDTA at 9 to 10 pH, the calcium and the magnesium forms stable colorless complex with EDTA. First of all, what we will do, the calcium and magnesium ions, these are present in the hard water. When it is reacted with a EBT. EBT means it is an indicator, areochrome black tea. And the pH conditions are 9 to 10. To maintain 9 to 10 pH, we will add the ammonium chloride along with the ammonium hydroxide. This is the buffer solution composition, ammonium chloride and ammonium hydroxide. This ammonium chloride and ammonium hydroxide will maintain the 9 to 10 pH. At these 9 to 10 pH conditions only the complex formation will take place. That's why we have to use the basic buffer. It will form the complex between the calcium and magnesium ions will form the complex between the indicator, EBT indicator. Is it unstable complex and the complex color is wine red. Okay. The complex which is formed between the calcium and magnesium and the EBT indicator is an unstable complex, and the color of the complex is the wine red color. Afterwards, what we will do, to the hard water sample, the blue color indicator EBT is added along with the ammonium chloride and ammonium hydroxide, as I told. Thus, EBT forms an unstable wine red complex with calcium and magnesium. After that, the unstable wine red color is obtained. This unstable wine red color is titrated against the EDTA, means ethylene diamine tetraesteric acid, which is taken in a burette. What will happen? This EDTA will replace the EBT, means the formed complex between the calcium and the EBT is an unstable complex. This unstable complex will be replaced by the EDTA, means the EBT, areochrome black tea indicator, will be replaced by the EDTA, chelating complex, means it will form the complexes with the metal ions like calcium and magnesium. Okay, this complex is a stable and colorless complex. This complex is a stable and colorless complex. But we will detect the endpoint from the wine red to blue. The endpoint of the titration is from the color change from wine red to blue. But the complex is colorless. The color of the blue is due to the free release of the EBT indicator into the water. Here the EBT is replaced by the EDTA. The EBT indicator will be released free into the water. Free indicator. This indicator will have the blue color. When the blue color is appeared, from winded to blue color will be appeared, we will stop the reaction. Means the reaction will be completed. Okay, this is what the principle of the EDTA titration. And next, the steps involved in the EDTA method or complexometric method. There are 4 important steps in the EDTA method. Preparation of MgSO4 solution, standardization of EDTA solution, determination of total hardness, determination of the permanent hardness. First step is the preparation of MgSO4 solution. MgSO4 we can take zinc sulfate, any standard solution we can take. First step, we have to weigh 0.25 grams of the MgSO4 and transfer it into a 100 ml standard flask through a funnel and dissolve the salt in a pure water, means distilled water. Here we have to take the distilled water only. Why? Because normal tap water will have the salts. These salts will form the reactions with the MgSO4. That's why we have to use the distilled water. Distilled water means it is free from salts and ions. Next, make up the solution up to the mark with distilled water and shake the flask for uniform concentration. Then calculate the molarity of MgSO4. After transferring the 0.25 grams MgSO4 into a 100 ml standard flask, we have to add little water and dissolve the salt. After dissolving the salt, the standard flask is made up into a 100 ml. Then we have to shake the flask for uniform concentration of the solution. Then we have to calculate the molarity of the MgSO4. Molarity of the MgSO4 is calculated by weight by gram molecular weight into 1000 by V. Weight by gram molecular weight into 1000 by V. Here weight of the MgSO4 is 0.25 grams. Gram molecular weight of the MgSO4 246.48 into 1000 by V. We are preparing for 100 ml, that's why here we are taking V equal to 100. If we calculate the value, M1 value is 0.01. We will get the M1 0.01. This is the first step, preparation of the MgSO4 and finding out the molarity of the MgSO4 solution. And next, step 2, standardization of the EDTA solution. After the preparation of MgSO4, we have to standardize the EDTA solution. Prepare out the 20 ml of the MgSO4 solution into a clean conical flask. This is the conical flask. Okay, we have to take out the MgSO4 solution which we have prepared in the step 1 with the help of a pipette, 20 ml, and it is transferred into a conical flask. Then add 2 ml of the buffer solution and 2 to 3 drops of the EBT indicator. After that, we have to add 2 ml of the buffer solution and 2 to 3 drops of the EBT indicator. I told earlier the buffer solution will maintain the pH of the 9 to 10, which is used for the complex formation, and 2 to 3 drops of the EBT indicator means it will indicate the color change. It gets wine red color solution. Take EDTA solution in a burette. After titrate with EDTA solution till wine red color changes to blue. After getting the wine red color, we have to titrate this wine red solution. Again is the EDTA. EDTA we have to take into a burette. Okay. We have to take EDTA solution in a burette. And we have to titrate the solution with the EDTA. Then what will happen? The color will change from wine red to blue. Wine red to blue. This is the end point. This is the end point. Here we have to stop the titration and we have to note down the reading in the burette. Here we have to substitute the values into the formula M2 equal to M1 V1 by V2. Here M1 equal to MgSO4 molarity, M2 equal to EDTA molarity, V1 equal to volume of MgSO4, V2 equal to volume of EDTA consumed. Here M2 we have to find out EDTA molarity. MgSO4 molarity we know 0.01 into volume of MgSO4 we have taken 20 ml. By volume of EDTA consumed, whatever the burette reading is the volume of the EDTA consumed. By substituting all these values in the formula, we will get the M2 molarity of the EDTA.